Yesterday we have seen three theorems, and first one was Cantor intersection theorem. Second one was if a continuous function is defined on bounded interval, then it is bounded. And the third one was a continuous function if defined on bounded interval is bounded and it attains its bounds. Okay. Do you have any doubt, difficulty, question in those proofs? Okay. Let us move and study a few more theorems related to properties of. हा आकाश जो आहे ना तो डेलिबरेटली उशिरा येतोय, त्याला जरा ठेवतो बाहेरच. आणि बाकी उशिरा आलेले नवीन पाहुणे जे आहेत तुमचं काय स्वागत करू का? बाकीच्यांचा वेळ वाया घालवता तर तुम्ही 5 मिनिटं आधी लॉग इन करून बसून जायचंय खुर्चीवर. नॉर्मली 10च्या आधी चालू करतो मी मीटिंग. आरामात आपले येत आहे, तुम्ही येईपर्यंत थांबून राहायला लागतं, परत स्क्रीन दाखवा, मी उशिरा आलो.
Excuse me, sir.
Yes.
Sir, in the proof to the second theorem yesterday, sir, I did not understand what the contradiction was for. In the
Function f, which is continuous in closed interval, a and b is bounded.
Yes, sir.
Okay. Let me.
So, what was the contradiction?
Yes, let me open the same screen, yesterday's screen. Let me pause recording now. Okay, in this proof, when we say that I1, I2, I3 we created, which are nested intervals, and In plus 1 is a subset of In. That means we are carrying out this process for a long time, and eventually we could catch element C by Cantor intersection theorem. That is where the limit will go and stop. It is not empty set, it is singleton, and we could catch hold of C, right? Now what we are trying to prove in this, because the function is continuous, what we are trying to show here is that the an comma bn set that you have produced, the an comma bn, which is the set which is being produced, is inside C minus delta to C plus delta. Okay, so what is C minus delta to C plus delta? What is this? Where this is coming into the picture? If the function f is continuous, then for a given epsilon, you will have value of the function within the epsilon limits of that function, value of the function. So f of c minus 1 is epsilon. So function will be between these two. Hey, what is happening? Why is this screen moving? Oh. Okay. So continuity of f says that at c minus, between c minus delta to c plus delta, the value of the function will move within epsilon limits of f of c. That is what we say here. Okay, and now what we are proving here is, as an is increasing sequence, bn is decreasing sequence, you can produce an comma bn interval within c minus delta to c plus delta, okay, where you have got unboundedness, and these two things contradict each other. this thing and this thing. See, this step f of x is bounded between f of x is bounded between f of c minus 1 and f of c plus 1 in the neighborhood of c, delta neighborhood of c. It is bounded between these two. Okay. And it is also said that between c minus delta to c plus delta, an and bn are inside. That means there exists a point c where the function is unbounded, because this an bn business that we have done is to catch the point where it is unbounded. Okay, so after that point we have considered the delta neighborhood and said that if it is a continuous, then it is well behaved like this. And simultaneously we are saying that between c minus delta to c plus delta, it is unbounded. That is where the contradiction is.
Okay, sir.
Okay. So now let me open the new screen. Theorem number 4. Bolzano-Weierstrass theorem. Statement. Let I be subset of R, some interval 1. Let F be defined from I to R. 2. Let F be continuous on I. 3. Let A comma B be four. F of A is greater than 0 and f of b is less than 0. Then 5. There exists C belonging to open interval a comma b such that f of c is equal to 0. This is very, very simple theorem because it is intuitive statement. If the value of the function is greater than 0 at a, if the value of the function is less than 0 at b, a is less than b, f is continuous, then you are bound to get at least one c in the open interval a comma b where the value of the function is going to be 0. Where function cannot jump and become negative. Function at a, if it is positive, it has to cross x-axis. Easy. Let us see how you put the proof in place. Intuitively, it is very clear. And with the results that we have already done in class, you should be able to write the proof. I wait for 4-5 minutes. The idea is that there is A, there is B, at A f of A is positive at b f of b is negative, and therefore you will have maybe one or two, I don't know, but let us have one point, and if the function is continuous, then you will have at least one c, which will give you the value of the function equal to 0. That is what this theorem is all about. So what we do is we take the bisection. Let C1 equal to a plus b by 2. Then f of C1 is greater than 0 or equal to 0, or it will be less than 0. If f of C1 equal to 0, theorem proved. If f of C1 greater than 0, choose interval C1 comma b. Let C2 is equal to C1 plus b by 2. Then f of C2 is greater than 0 or equal to 0 or less than 0. If f of C2 is equal to 0, theorem proved. If let 9, theorem proved. If f of C2, let us take, is less than 0, choose interval C1 C2 dot dot dot. Let us name these intervals. First one is I, second one is I1, this is I2, and so on. Therefore, now instead of open interval showing, I can always show them as closed interval, because the values of the functions at the boundaries are known to us, and let us fabricate situation for application of Cantor intersection theorem. This implies I1, I2 dot dot dot. Okay. Therefore, by Cantor intersection theorem, limit Cn plus 1 minus C1, Cn as it tends to infinity is equal to 0. नाही काय करायचं आपल्याला, ओके सॉरी लिमिट लिहायचीच गरज नाही. बाय कॅन्टर इंटरसेक्शन थेरम, intersection of n greater than equal to 1 in is equal to C. So you will be able to catch an element C such that it is part of each set. Now, if f of C is greater than 0, contradiction to above. Let us on Cantor intersection theorem, because Cantor intersection theorem says that you take these nested intervals up to infinity so that you catch hold of singleton point 1. Now, if f of C is greater than 0, then you have not arrived at that point correctly. Is that right? Is that correct statement? Is it contradiction to Cantor intersection theorem?
If it is greater than 1, if it is greater than 0, then we can say that we can again take an interval.
Yes, but then that is what I mean when we say that we have reached the stage where we have caught hold of C. I think we have exhausted all the possibilities.
Yes, sir.
Therefore, it cannot be greater than 0, contradiction. If f of C is less than 0, contradiction. Therefore, f of C must be equal to 0. Theorem proved. Simple. I mean, if we understand it correctly, we write it whatever our understanding is, and that is what is going to be the proof finally. Tell me if there is any doubt in anybody's mind. Because if f of C is greater than 0, then this C itself is a starting point. C comma B is a starting point of this theorem. That is where we started. C comma B. So you do these iterations and you arrive at new C, where you cannot afford to have it greater than 0, you cannot afford to have it less than 0. So if f of C is greater than 0, then the starting point of the theorem could be this. If f of C is less than 0, then you are talking about a comma C. That is where we should start. But we have already started earlier using a comma B and arrived at C. Therefore, this is not possible. This is not possible. Therefore, there is no choice for C to be equal to 0. Okay. Next. Have you?
Sir, can you once show the whole screen?
Yes. That
Thank
is
you,
a
sir.
good idea. This is Bolzano Westrauss. Yeah. I mean, nothing great about it, but only greatness of these people are they were born much before us. Theorem number 5, properties of continuous functions. Intermediate value theorem. This is one of the most important theorems in differential calculus. Let I be equal to a comma b, closed interval a comma b. Let f be defined from a comma b to r. If f is continuous on I and f of a is less than f of b, then for every k such that f of a is less than k is less than f of b, there exists c belonging to closed interval a comma b such that f of c is equal to k. So the geometry of this is, suppose a value of the function f of a, b value of the function f of b, and f of a is less than f of b as shown in the diagram, and the function is something like this, suppose. Then for every k which is between f of a and f of b, that is any value between these two k, you will find, suppose I take this value, I go to function, I get this, and this is my c. If I want this value, you go to function and project, you will this. So this theorem, intermediate value theorem, says that for every value between the two extreme values of the function, c which will give you that value. I mean, it is very simple. It is simple. But writing proof is now an art. And intuitively you understand the theorem, but you need to develop skill to convert your intuition into the proof. Intuition into proof. Draw diagrams into proofs. You have to get it. Now this is something which is doable for you. So try your level best. Already. Okay, now in this proof, what we are supposed to use is previously proved theorem, which is Bolzano-Weierstrass. Therefore, proof. We have to create situation such that the prerequisite conditions of Bolzano-Weierstrass theorem are satisfied, and hence we directly use it. There it is required to be continuous, one extreme of function should be positive, another extreme should be negative. That is what we want. If we can create a situation like that in intermediate value theorem, we will be able to do it, and it is very simple because it is given that f of a is less than k is less than f of b. So consider g of x is equal to f of x minus k, as f of x is continuous and k is continuous, that is y is equal to k. These two y is equal to f of x is continuous and k y is equal to k is continuous. G of x is continuous over closed interval a comma b. G of a is equal to f of a minus k is less than 0, and g of b is equal to f of b minus k is greater than 0. Hence, Bolzano-Weierstrass. theorem can be applied, which implies there exists C belonging to open interval a comma b such that f of c is equal to, sorry, such that g of c is equal to 0, implies f of c minus k should be equal to 0, implies f of c is equal to k. Theorem proved. These are simple ideas, but very, very useful eventually. Any doubt, difficulty you can ask? Meanwhile, I go to the next concept. Sixth, we have to understand meaning of sign of derivative at point. Let C be an interior point of the domain of function f. Let derivative of f at c exists and is positive. That is, f dash of c is greater than 0. Okay, so if this is the situation, what do we understand? Now, at c, whatever that function is, bad, whatever that function is, at c, it is given that derivative exists and it's positive. So geometrically we say that, okay, there exists a tangent which can be drawn and it has got slope which is positive. So meaning of that, if the derivative is positive, what is the meaning of that? First we have to understand, first we have to think and find out what is the meaning, and then if our thinking is correct, we have to write mathematically why it is correct. Okay, so I give you 4-5 minutes to think about it and come up. I mean, thinking is easy, but then coming up with the algebraic proof why your thinking is correct is necessary. Do it. What is given to us? F dash of c is greater than 0. Means f dash of c is greater than 0 means limit as x tends to c, f of x minus f of c upon x minus c is equal to f dash of c, which is greater than 0. This is what is given to us. That is the meaning of f dash of c. So if we really find out the meaning of limit, then let epsilon greater than 0 for epsilon greater than 0, there exists delta. greater than 0 such that what is the limit definition? F of x minus f of c upon x minus c minus f dash of c, absolute value should be less than epsilon for when x is such that 0 is less than x minus c is less than delta. This is what is our definition of limit. Okay, so if this is the definition, what is the other meaning of this definition? Other meaning is this implies f dash of c minus epsilon is less than f of x minus f of c upon x minus c is less than f dash of c plus epsilon. Okay, that is for all the x within the delta. For every x belonging to c minus delta to c plus delta. This is the other meaning of this. बरोबर चल रहा है? Therefore, what do we do now? I mean, there exists epsilon. I mean, we can put condition on epsilon such that it is less than f dash of c. So this is positive. This is also positive. Therefore, this quantity is also positive. If epsilon is chosen positive, sorry, not positive, less than f dash of c, then f of x minus f of c upon x minus c is going to be greater than 0 for every x belonging to c minus delta to c plus delta. That is where we arrive at the sign of this ratio. Many of you have started with this, but then this is what is the background, how you arrive at this ratio being positive. Okay, so now we are clear about it. So if x belongs to c minus delta to c minus delta to c, so x is to the left of c, that means implies x minus c is less than 0, implies f of x minus f of c is less than 0, implies f of x is less than f of c. If x belongs to c comma c plus delta, x minus c is greater than 0, implies f of x minus f of c is greater than 0, implies f of x is greater than f of c. Now, these two statements imply that therefore, this implies if x belongs to c minus delta to c plus delta, f of x is increasing. At x is equal to c. This is very important. If f dash of x is positive in the delta neighborhood of c, you will find the function increasing. That means if you go to the left of c, the value of the function will be less than at f of c. If you go to right of c, the value of the function will be more than f of c, and hence we call such function as increasing function. Okay? So that is what is the meaning. Similar proof can be given. Similarly, if f dash of c is less than 0, then f of x is decreasing at x is equal to c. That is what is the meaning of the sign of derivative. Namaste. Good. So, next thing. I make it little small, push it up so that you can complete your writing, and I complete my writing next theorem. Violet. Theorem number 7. Rolle's theorem. Okay, before writing the statement of the theorem, I would like to take out the statement of the theorem from you by giving a couple of examples. So let me know the moment you finish writing. Okay. Now, I have a function a, b, and the value of the function at a and at b, it is same. And it is given f is continuous. Between over a comma b, closed interval a comma b, and it is given f is differentiable over open interval a comma b. So if I start from this point, if I want continuity and differentiability, in how many ways I can reach here? Many ways. I can go like this, I can go like this, I can go like this. Okay? I can go like this, I can go like this. Okay. There are many ways I can go to be being continuous and differentiable. Okay. So if I find out infinitely many ways of starting from A to B, what is the most common thing which is happening in all these functions? That is what you write down on your notebook and show me. I mean, what is so good about this? If it is continuous and differentiable, and value of the functions at both the extreme points of the interval, if they are same, then what is the good thing which is happening and is going to be always true? Okay, so the statement of Rolle's theorem is if a function f with domain closed interval a comma b is continuous in that domain, differentiable in open interval a comma b, f of a is equal to f of b, then there exists c belonging to open interval a comma b such that f dash of c is equal to 0. That is what is the statement of Rolle's theorem, and we have observed that in the geometry, if we really try to sketch the function, we find that at some point or the other, the tangent must become horizontal. That is what is being captured in the statement of the theorem. I wait for 7-8 minutes for you guys to write the proof of this. After that, I will write. Pause. Okay, let us write the proof of Rolle's theorem. Proof. As function is continuous and bounded over a comma b, it attains its bounds. Let capital M be maximum and small m be minimum. Let C belong C comma D be such that f of C is equal to capital M and f of D is equal to small m. Case 1. Capital M is equal to small m implies f of x is equal to capital M for every x belonging to open interval a comma b, implies f dash of x is equal to 0. Actually, everywhere it is going to be 0 because it is going to be constant. If maximum equals minimum, then it is a constant function, and therefore f dash of x is going to be 0. Proved. Case 2. Capital M is not equal to small m. Therefore, there will be at least one of capital M comma small m different from f of a comma f of b. Why? Because f of a and f of b are equal and m is not equal to small m. Therefore, either capital M's. Now, if you have a graph like this, then this is minimum. F of a is equal to f of b is equal to small m. So capital M is somewhere else. Understood? If the graph is like this, then capital M is equal to f of a is equal to f of b. You have small m somewhere else. So at least one of capital M comma small m is going to be different than f of a comma f of b. Without loss of generality, let capital M is not equal to f of a, is equal to f of b. Okay? Let f of c is equal to capital M which is not equal to f of a, implies c is not equal to a. f of c is equal to capital M, which is not equal to f of b, implies c is not equal to b. Therefore, a is less than c is less than b. C is there in between. If f dash at c is greater than 0, then there exists delta greater than 0 such that for every x belonging to c comma c plus delta, what do you have? F of x is greater than f of c. If f dash of c is less than 0, then that is what is meaning of sign. That is 6th number. Okay. If f dash of c is less than 0, then there exists delta greater than 0 such that for every x belonging to no, wait. Okay, let me have both open enter c minus delta to c f of x is less than 9. काय पाहिजे इथे? If f dash of x is less than 0, that means it is decreasing function, and to the left of c,
To the left of c, f of x will be greater than f of c.
f of x is going to be greater than,
but f of c is maximum, so there will be contradiction.
f of c. Now, yeah, so f of x is greater than f of c, contradiction to maximum. I mean, is equal to, actually this is f of c is equal to m. That is the maximum value, contradiction. And f of x is greater than f of c, which is equal to m, again contradiction. Right? Therefore, this implies f of c must be equal to 0. Theorem proved. I think it is simple. Only complication here is to catch hold of that point C where either maximum or minimum is happening and it is other than a comma b. That is the only complication which we should clearly write. Okay, write down the proof. Okay, let us do some examples. Question 1. I have to keep it at 50%. Okay. The equation e raised to x minus 1 plus x minus 2 is equal to 0 has one real root, two, 3, 4. Show me your answer. Okay. Okay, so the answer is only one real root. Now, because we have learned Rolle's theorem just now, let me write the answer using Rolle's theorem. Answer. Let x is equal to 1, f of x is equal to 0. This is f of x. So x is equal to 1 is a solution. If possible, let f of x is equal to 0 has another root equal to alpha, which implies f of 1 is equal to f of alpha is equal to 0, correct? F of x is continuous. F of x is differentiable over 1 comma alpha over 1 comma alpha. Therefore, by Rolle's theorem, there exists C belonging to 1 comma alpha such that f dash of C is equal to 0, correct? So f dash of x is equal to e raised to x minus 1 plus 1, right? Is going to be always greater than 0 because e raised to x minus 1 is above x-axis and you are adding 1 to it is always going to be greater than 0. Therefore, contradiction. You want f dash of c to be 0 and it is always going to be greater than 1. Therefore, only one real root. Okay? This is the correct logical explanation. Okay, next problem. If 2a plus 3b plus 6c is equal to 0, then at least one root of the equation ax square plus bx is equal to 0 lies in the interval a 2 comma 3 b 1 comma 2 c 0 comma 1 d 1 comma 3. Okay. Because we have learnt Rolle's theorem today, this question must be on Rolle's theorem. Otherwise, it is going to be extremely difficult in general if it is asked. Okay, so let us solve. Given 2a plus 3b plus 6c is equal to, if we divide everything by 6, we get a by 3 plus b by 2 plus c is equal to 0. Now consider is very difficult step. F of x is equal to ax cube upon 3 plus bx square upon 2 plus cx. Consider this function plus cx. Okay. Now actually after considering this, why should we consider this function? Because we have got this relationship with us. And there is a possibility that by putting some values of x into it, we end up getting 0. It is very obvious that if we put these two extreme values 0 and 1 in this equation, so f of 0 is 0 and f of 1 is also 0. In any other intervals, it is not going to happen. Okay, but independent of knowing the values of ABC, if we put 0 in this equation and 1 in this equation, there it's a polynomial function. F of x is polynomial, therefore it is continuous and differentiable. Hence all requirements of Rolle's theorem are applicable. Correct? Therefore, now we are considering this function for x belonging to closed interval 0, 1. Okay, we find this is equal to 0. So there will exist alpha 0 such that 0 is less than alpha is less than 1. Barabar? Therefore, alpha is a root. What is f dash of x? F dash of x is equal to 3ax square upon 3 plus 2bx upon 2 plus c. Correct? Therefore, this is equal to ax square plus bx plus c. That is what is asked. F dash of x is equal to this lies in that at least one of the equation.
One root of the equation.
One root of the equation lies in the interval. Have you understood? This becomes 0 at alpha. Therefore, at least one lies in this interval. So the game is this. This makes f of 1 equal to 0 and suitable for Rolle's theorem. Applying Rolle's theorem. Therefore, f dash of alpha is equal to 0 and hence we have at least one root between 0 to 1. Option C. Okay, write down the solution. That is where we stop for today.